All right, taking a look at lesson 59, using fractional exponents. Going through this lesson, it's going to look a lot harder than it actually is. Just you guys will start to get used to some of the notation after a while, and hopefully this will be a successful video for you guys. It'll help you out a little bit. In the expression x to the AB, a plus b, or a plus b, I should have said, a plus b is the exponent. That's what we're dealing with. A little refresher here, remember negative exponents. If we're going to simplify this, negative exponents change the position. If it's in the denominator, now it's going to go up to the numerator. So that's going to add an x. So that's going to be x to the third. And the y's, that's actually going to cancel out every y except for 1. So I'll actually cancel it out like that. So that's x to the third times y all over 1, or just x to the third y. And then lastly, if we were going to solve, the square root of x is equal to 4. We can square that, square both sides. We get x is equal to 16. Moving right along, exponents in the form m over n, where m and n are integers and n is not equal to 0, are called rational exponents. Rational exponents can be written as radical expressions. So this is a pretty important concept for you guys. So probably the most common one that you will have seen is dealing with a square root. So if we have the square root of x, do not forget that this can be written as x to the 1/2 power, because depending on the problem, just that switch in notation can help out so much. And then that second little definition piece, you see they kind of spice it up a little bit more. So now we have m over n. So let's say we have x to the 3/2 power. So now we're taking a square root of x. However, that x is being raised to the 3rd power. So the top number is the power that's going to go with the base, in this case an x, and the denominator of that exponent is what power of a root that we will take. So this would be the square root of x cubed, is what that would look like. Just to give you another example, if you don't like their m over n and a and everything like that. So first example, we're just simply going to rewrite these as radical expressions. Okay, so if I have 3 to the 1/5, remember, so a 3, we can even think of it this way. A 3 is being raised to the 1st power, and the power of our root is 5. So this is going to be equal to the 5th root of 3, is what that would look like. And then the part B, our base is 9, our root is the 4th root, so this is going to be the 4th root of 9, and then that 9 is to the 3rd power. Moving right along. Alright, some properties. There's a lot of properties that go along with exponents. They can be easily confused. So on the next slide, if you need to, pause it, write them down. That would be very beneficial. And it looks like some stuff didn't copy over in formatting very nicely over here. So I'll do my best. Radical expressions in the form, the nth root of a, are called nth roots. In this form, n is the index and a is the radicand. Similar to square roots, a to the nth root is equal to b to the n is equal to a. When nth roots have an odd index, there is only one real root that maintains the sign of the radicand. For example, the cubed root of 8 is equal to 2, and the cubed root of negative 8 is equal to negative 2. When the nth roots have an even index, and the positive radicand, there are two real roots, one positive and one negative. For example, the fourth root of 16 is equal to plus or minus 2 with an even index, and a negative radicand has no real roots. So keep that in mind. If that didn't make sense, here's essentially what it's saying. If we have an even index, so if we took, let's say I was just doing a square root again, because that's the easiest thing, that's what we're most familiar with. We know that we can't do the negative square root of 16, even though the positive square root is 4, or we should know by now that's plus or minus 4. However, we can't do negative square roots, and that doesn't only go with square roots, that goes with any even index number, so fourth roots, sixth roots, eighth roots, so on and so forth. Couple properties right here. The product property. So if we're taking the nth root of two things that are being multiplied, we can split those apart. And likewise, if we are dividing two things in the nth root, we can split those apart so that we have one in the numerator, one in the denominator. Notice those n's stay the same. That means the power of that root stays consistent throughout the entire thing. So for this first one, it looks like we're going to be using that product property. So I want to split up my numbers with my variables, and then we can put them back together in the end if it seems fitting to do so. So this would be the same as the fifth root of 243 times the fifth root of x to the 10th. Now, with our properties that we've learned so far, the fifth root of 243 is one that we can simply evaluate. Once you guys start working with roots more often, things will become more familiar to you. The fifth root of 243 is actually 3. And then the fifth root of x to the 10th, we should be able to rewrite this. So if we were rewriting this as a power, that would be equal to x to the 10 over 5. And then we can simplify these. So if we have x to the 10 over 5, that is just x squared. So our answer for that first one is just 3x squared. Now in that second one, just like our last property said, if we have a radical over two things, that is, or over an entire fraction, we can split that apart. Now, this concept right here that I'm going to show you is going to seem a little bizarre, but bear with me for just a second. So the top is not that difficult because we have the fifth root of x to the 5th. So those fifths will cancel each other out, so we're just dealing with an x on top. However, we have a fifth root of 2. Now here's the bizarre part. So we know that we cannot have radicals in the denominator. So let me simplify this really quick. Now in a square root, I would just multiply that by another square root 2. However, we are taking a fifth root. So what that means is that we need 5 root 2's on the bottom in order to get a 2. So in a square root, let me take a little side note, square root of 4 times square root of 4 equals 4. And that's because we get square root of 16, and square root of 16 is 4. So same type of property. If we have, remember I said that those will cancel out on top, because we have that fifth root. We're going to need 5 of them total in order to make a real number 2. So I'm going to multiply by fifth root of 2. I have 3, 4, 5. and I'm going to match those with the ones that I've added on. Okay, so on the bottom, what we have here is just a 2. Now on the top we have that x, and I don't want to rewrite all of these as all of those spread out. So they're all the same thing. So the way that I can rewrite that so it's a little more condensed is I can say the 5th root of 2 to the 4th power. So that will be my final answer right here. All right, now here is the properties that you should probably take a look at, and I would pause the video, take a minute to look these over, because you're going to be using all of these properties in the next couple of problems or so. Zero exponent property, remember anything to the 0 power is 1. Negative exponents, change the place. If you have the same base, you have 2 things of the same base, we can rewrite those as a single thing where we are adding those exponents together. Kind of the same thing with division, only if we're dividing we're going to subtract. That's the quotient of powers property, power of a power property. So if you are taking it, you have an exponent and it's being raised to another power, you're going to multiply those. Power of a product, you can break those apart. Quotient, power of a quotient, you can break those apart and have everything raised to powers. All right. So based on what we were just going through, I have the same base for both of these. So that means I should be able to rewrite this as 64 to the 7/16 plus 1/16. Okay, so that should help me out. 7/16 plus 1/16 is 8/16. 8/16 is a half. So I have 64 to the 1/2 power. I know that 1/2 is the same as the square root, so this is asking me for the square root of 64, which we all are familiar with as being 8, or in this case, plus or minus 8. All right, let's look at part B. Again, we have 2 things that are of the same base, so this can be written as 16 to the 6/4 minus 7/4. So that's going to leave me with 16 to the negative 1/4 power. Now, if I have a negative, that's going to move me down to the bottom, so that turns this into a fraction, and 16 to the 1/4 power. That would be the same as taking a 4th root. Fourth root of 16 will be 1 over plus or minus 2. Okay, so keep your properties straight, work through them one at a time, problem solve, and these shouldn't be too bad. Moving along here, we have 12 to the 10th to the 1/5, so we have powers of powers. This is going to be, since we have 1 is a fraction, we're multiplying those together. So if I multiply those, that's the same as taking 12 over 5. So this is going to be 12 squared, which is 144. All right. Go back real quick. So this one is going to be, this last one is dealing with this piece right here. So we have 2 things that are being multiplied, taken to the 1/3 power. So that means I'm going to do 27 to the 1/3 power times 125 to the 1/3 power. 27 to the 1/3 power is the same as taking a cubed root of 27 times a cubed root of 125. This is going to be 3 times 5, which equals 15. like I said, if you get comfortable with these properties and everything, these problems become a lot easier. All right, now if we are going to solve. So it might be more beneficial for you to look at these things in a different way. For me personally, I would rather look at this as the cubed root of x is equal to 6, so that I know that I'm taking that to the third power. So that would give us x equals 6 times 6 is 36, times 6 is 216. Next one. Oh, solving here. So anytime you're taking a power, or if you have fractions the way that we do here, we could raise that to the opposite and that would undo it. So if I multiplied this by the 5/4 power, then I just have an x, and that actually makes this more solvable over here, because let me help you out with this a little bit. So 16 to the 5/4 power, you can evaluate those in whatever way is more beneficial to you. So I already know what 16 to the 1/4 power is. So I'm going to think of it this way. I'm going to evaluate that to the 1/4 power, and then I'll take that answer to the 5th power. So 16 to the 1/4 power I know is 2 raised to the 5th is going to be, let's see, 2 to the 3rd is 8, 16, we'd get 32. And then the last one, we can do that same thing again. We can take that to the 3/4 power. So that leaves us with an x. I don't know what the 4th root of 7 is, but 7 times 7 is 49. Let's do 49 times 7. We would get 63, 28, 34, 343. So x is equal to the 4th root of 343. Let's check some numbers. I wonder if that's going to be 4. So 4 times, that'd be 256. Let's take a minute. There's actually not going to be anything that's going to be special about that. That'll just be x equals the 4th root of 343. All right, we got one more. In the Netherlands, the city of Rotterdam has a complex of cubic homes designed by the Dutch architect Piet Blom. Each home has a side length of 7.5 meters. Use the equation where y equals the cubed root of v, and again, I'm pretty sure this got messed up again. Length and v is volume. So essentially what we want to do here is if each side length is that and we have cubic homes, that's going to be y would be our side length. So I'd have 7.5 is equal to this, because we would have, if it's a cube, and each of those is going to be 7.5, we could cube that in order to get our volume. So let's see, 7.5 cubed would give us a v, which would be 421.875. Okay, I know this one ran a little bit longer, But I hope you guys benefited from this. Like I said, I hope you were able to pause it and take a minute just to get some of those properties written down so you can be more comfortable with them.